So today I'm going to present Polyhedral Computation in Julia. So I first explain what this is. So it's better explained by just this picture. So what we always have to do in Polyhedral Computation is, suppose you have a cloud of points and you want to obtain the convex field of this cloud of points. And once you obtain the convex field of this cloud of point, which is shown in blue, you can actually represent it by all its faces. And all these faces in 3D, these are planes, but in higher dimensions, these are hyperplanes. So basically, this description says here's a list of hyperplanes. The polyhedron is on that side of all these hyperplanes. So for every hyperplanes, you have a side. And so you have this kind of dual description, the V representation with the points and the H representation with the hyperplanes. And so this is very useful. For example, it's used in reachability analysis for computing invariant sets. The Delaunay tessellation is actually a parameter that's closely related. It's also used in game theory, and optimization is also very important because, for example, when you do mixed integer linear programming, the ideal formulation you want to do is you take all the integer points of your problem, and when you take the H representation of that, it gives you all the constraints that you should give to jump, so that if you remove the integrality constraints, you still have only the integrality points as optimal solutions. So it's used in many problems, and there are actually many different libraries that exist. So there are CDD, LRS, QHUL, and so on. These are usually written in C or C++. And then there are also no implementation in pure Julia as well. Now, one paper that I really like, which is this one from 1995, showed that actually what's tricky with this is that there is no best method for everything. Actually, these different libraries, they can be described with 3 different algorithms. There is the double description one, the reverse search one, and the quick fill one. And actually, depending on your polyhedron, so if you read that paper, then to tell you which property of the polyhedron actually matters. And so depending on the class of polyhedra that you have, one of the 3 is going to be much better asymptotically to the other one. And if you look at it, like the implementation is not so important here, of course, to which one is going to be faster. It's really the complexity. Even the ones that are using rational big int as arithmetic, so they are, of course, they are much slower to do every single operation, but are still going to beat the one in floating 64 or in rational of int if just because the algorithm is better suited. So because of that, if you look at actually some libraries to compute invariant sets in some other languages, they actually have a hard-coded fixed library that they are going to use for every operation that they need to do. And so in a sense, while you already know in advance that this is not going to work for some use case, because on some use case you might have a polyhedron in the class where double description is very bad. And so it's very important whenever you design an algorithm that's going to require doing polyhedral computation that you do not hard-code the library that you are going to use, because then there is always one user that will use one instance for which your algorithm then is going to be not good. So you always want to parameterize your algorithm on the library so that the user can then, for your case, try all the libraries and then choose the one for which his class of polyhedron is going to be fast for its class. So it's important to parameterize that, and I mean the user doesn't have to see in which class it is, he can just try all the possibilities. And so a second aspect that is quite challenging for this is that actually in all the different operations that you can do, so you see that you have these 2 representations for polyhedron. It's actually quite computationally intensive to go from the vertex representation to the hyperplane and vice versa. And actually, usually, sometimes when you do some operation, you need to be in one of the 2 representations. And sometimes you create it in the V representation, but then maybe you want to take some intersection, so you need to convert to the H representation, and so the intersection would be in H representation, and then the user might want to multiply this intersection by a matrix, so then you need to be in V representation and so on. that all this bookkeeping of doing this representation conversion at the right time, but not when it's not needed, it's making the code very complex. And so the goal of Polyhedra was to try to make this all transparent. And so in the Polyhedral.jl package, we have the V and H representation that you can describe. H representation, you can easily obtain it from a jump model. And then the polyhedron type, it kind of contains the two, but maybe it contains only the H, maybe only the V, or maybe both. And it's going to, depending on which operation you do, trying to automatically convert when needed. And trying to make this transparent, but it's also easy to see what it has done. And then, so we have this interface, and then we've tried to wrap all the different libraries in Julia with the same interface, so that when you build a polyhedron, you can say which library you want underneath, and then, because you use this abstract interface, your code is not actually going to depend on which library you use, but depending on the library, what's happening underneath is going to be very different. So that's it.
Thank you very much. Do you have any questions? Yes, please.
Maybe a kind of weird question, but do you have any idea how to simplify multidimensional polyhedra? Whatever simplify means, like getting a representation, like for example, less vertices or less half spaces defined.
So this is going to depend a lot on what kind of operation you want to do on this polyhedron.
An optimization problem, and it's a feasible region, and a feasible region is too complicated, so I want to kind of simplify the feasible region.
Yes. So this is something that happens a lot. So when you do mixed integer linear programming, usually the feasible set you want to use, because it's a feasible set for which when you remove the integrity constraint, you will only find integer solution. These sometimes have way too many half spaces. And so typically what you can do is that you sometimes do not give some of these constraints, and you might give them later with jump with like lazy constraints. But another approach that's very common is to try to lift the space, because sometimes the polyhedron is very complicated because it's a new variable, increasing the dimension. You find the representation of your polyhedron with much less faces. And your polyhedron that you had initially is just the projection. And when you do the projection operation, so I had it on the previous slide, you can see that for the hrep, it's a red arrow. What I mean by red here is that it's going to be not ideal. So projection is easy to do for the V representation, because the projection has basically as many points and many vertices, or maybe even less if they are projected to 0. But from the H representation, when you project, the number of vertices can grow significantly. It's the Fourier-Motzkin algorithm, and for every dimension that you project, it can explode.
Let's thank Benoît one more time.